Planck epoch, t approximately 10 to the negative 43rd seconds. At the very dawn of time, so close to zero that our clocks have no resolution, the universe existed in a state where quantum mechanics and gravity fused into a single, unfathomable tapestry. This unimaginably brief interval, known as the Planck epoch, is defined by the Planck time, approximately 5.4 times 10 to the negative 44th seconds, the shortest meaningful unit of time. Within this sliver of existence, the energy density reached the Planck energy scale, approximately 1.22 times 10 to the power of 19 gigaelectronvolts, and space-time itself was subject to violent quantum fluctuations. In such a regime, the smooth fabric of general relativity dissolves into a roiling quantum foam, where virtual black holes might pop in and out of existence, and notions of distance or duration lose conventional meaning. Our current theories, general relativity for the cosmic and quantum field theory for the subatomic, both break down here. Physicists posit that a quantum theory of gravity, perhaps string theory or loop quantum gravity, is needed to describe this frontier. Philosophically, the Planck epoch represents the ultimate boundary of what we can know, the moment at which, before the Big Bang, might itself be an ill-defined concept. It beckons us toward new physics, reminding us that every answer in science opens doors to fresh mysteries. Grand Unification Epoch, t approximately 10 to the power of negative 43 to 10 to the power of negative 36 seconds. Emerging from the quantum turmoil of the Planck era, the universe cooled just enough for the gravitational force to freeze out, leaving the strong, weak, and electromagnetic forces still entwined as a single, grandly unified interaction. This Grand Unification Epoch is the realm of hypothetical guts. Grand unified theories, often formulated in symmetry groups like SU5 or SO10. At energies exceeding approximately 10 to the power of 16 GeV, the three forces behave indistinguishably, mediated by exotic gauge bosons, frequently dubbed X and Y particles. As the cosmos expanded and cooled toward 10 to the negative 36 seconds, the unified interaction fractured. The strong nuclear force parted ways with the electroweak force. This symmetry-breaking event set the stage for the rich tapestry of particle physics we observe today. Yet the precise gut that governs this epoch remains hidden. Proton decay, a telltale signature predicted by many models, has never been seen, constraining the landscape of viable theories. Thus, the Grand Unification Epoch stands as both a triumph of theoretical elegance and a challenge to experimental ingenuity. Strong force separation, t approximately 10 to the negative 36 seconds. At roughly 1/1,000,000,000 of a second after time zero, the strong nuclear force ripped away from its electroweak partners. This decoupling endowed quarks with the property of confinement. They would henceforth bind tightly into composite particles, hadrons, rather than wandering freely. The mediator of this force, the gluon, became the glue that holds protons, neutrons, and heavier nuclei together. This symmetry breaking is more than a technical footnote. It imprinted the universe with the seeds of all atomic structure. Without quark confinement, no atoms, no chemistry, nor life could exist. The dynamics of this transition involve the formation of a quark-gluon plasma, a seething soup where quarks and gluons intermingle, presaging the conditions recreated in modern particle colliders like the Large Hadron Collider, LHC, and the relativistic Heavy Ion Collider, RHIC. In studying these extreme states, we peer back to that primordial split when force itself diversified. Onset of inflation, t approximately 10 to the negative 36 seconds. Just as the strong force etched its identity upon the cosmos, another dramatic chapter began: cosmic inflation. First proposed by Alan Guth, Andre Linde, and others, inflation describes a fleeting epoch in which space itself expanded exponentially, doubling in size perhaps 60 times or more in less than 10 to the negative 32 seconds. Imagine a microscopic bubble inflating to the size of our solar system in an instant. This is the scale of inflation's fury. Driven by a hypothetical inflaton field perched in a high-potential energy state, inflation smoothed out any primordial wrinkles and stretched quantum fluctuations to astronomical scales. These magnified fluctuations would later become the seeds of galaxies, clusters, and the large-scale structure of the universe. Emotionally, inflation feels like a cosmic heartbeat, a brief, monumental pulse that imprinted order on chaos. Though the exact nature of the inflaton remains elusive, its fingerprints are written across the sky in the cosmic microwave background. Inflation's effects: smoothing and flattening. The inflationary burst accomplished two of cosmology's most perplexing feats. It resolved the horizon problem, why regions separated by vast distances share nearly identical temperatures, and the flatness problem, why the universe's spatial geometry is so closely balanced between open and closed. By stretching space so dramatically, inflation carried tiny, causally connected patches to scales beyond our observable horizon, ensuring uniformity. Simultaneously, any intrinsic curvature was driven towards zero, rendering space effectively flat. Beyond these engineering marvels, inflation also provided a mechanism for structure formation. Quantum jitters, normally confined to subatomic realms, were flung across the cosmos, freezing in as minute density variations. Billions of years later, gravity amplified these ripples into the cosmic web of galaxies. It's a breathtaking synthesis of the quantum and the cosmic, the same uncertainty that limits our knowledge of a particle's position, birthed the very architecture of the universe. End of inflation and reheating. T approximately 10 to the negative 32 seconds. Inevitably, the inflaton field rolled down its potential, and inflation drew to a close. This slow roll termination unleashed pent-up energy in a process known as reheating. The inflaton decayed into a swarm of elementary particles, quarks, leptons, gauge bosons, and the universe became a furnace of unimaginable heat, with temperatures rebounding to approximately 10 to the power of 27 Kelvin or more. Reheating repopulated the cosmos with the ingredients for all future complexity, the particles that would form atoms, stars, and eventually life. In literary terms, if inflation is the calm, expansive breath before creation, reheating is the fiery exhale that remakes the universe's content. It's the transition from the abstract potential of the inflaton to the concrete reality of matter and radiation, a cosmic alchemy that set the stage for every subsequent epoch. Quark-gluon plasma and thermalization. In the immediate aftermath of reheating, the universe existed as a quark-gluon plasma, QGP, a state in which quarks and gluons roamed freely in a dense, hot sea. Temperatures exceeded trillions of kelvins, and the distinction between individual particles blurred. This primordial plasma persisted for microseconds, far shorter than a blink of an eye, but long enough for thermal equilibrium to establish. As expansion continued, the plasma cooled to thresholds where quarks could no longer overcome the strong force's confining grip. This thermalization process marked the beginning of hadronization. Quarks coalesced into protons, neutrons, and other hadrons. Modern heavy ion experiments recreate QGP conditions to study this exotic state, allowing us to glimpse the universe's first microseconds in a terrestrial laboratory. Baryogenesis. Matter-antimatter asymmetry. One of the deepest puzzles in cosmology is why matter prevailed over antimatter. In principle, the Big Bang should have created equal quantities of both, leading to mutual annihilation and a universe suffused only with photons. Yet we exist in a cosmos teeming with matter. The epoch of baryogenesis, a process occurring roughly between reheating and Big Bang nucleosynthesis, introduced a slight excess of baryons, approximately 1 extra particle per billion pairs. To generate this asymmetry, 3 conditions outlined by Sakharov must be met: baryon number violation, C and CP symmetry violation, and departure from thermal equilibrium. While the standard model embeds some CP violation, it appears insufficient, hinting at new physics. Baryogenesis remains an active frontier. Leptogenesis, where an initial lepton asymmetry converts into baryons, and gut-scale processes vie as explanations. This tiny imbalance, a mere whisper in the cosmic symphony, enabled the existence of galaxies, stars, planets, and ultimately life. Electroweak Epoch, T approximately 10 to the power of minus 36 to 10 to the power of minus 12 seconds. After the dust of reheating settled, the universe entered the Electroweak Epoch. Here, the electromagnetic and weak nuclear forces existed as 2 facets of a unified electroweak interaction, governed by symmetry group SU 2 times U1. The W and Z bosons and the photon shared a common genesis, and particles acquired mass only once this symmetry broke. Temperatures during this epoch soared above approximately 100 GeV, and the Higgs field had not yet settled into its non-zero vacuum expectation value. Particle interactions were governed by high-energy electroweak processes, with frequent creation and annihilation of WZ, quanta, quarks, leptons, and the Higgs boson itself. Study of electroweak unification underpins much of modern particle physics and was spectacularly validated by the discovery of the W and Z bosons in the 1980s at CERN and the Higgs boson in 2012 at the LHC. Electroweak symmetry breaking, T approximately 10 to the minus 12 seconds. At around 10 to the minus 12 seconds, the Higgs field underwent a phase transition, acquiring a non-zero vacuum expectation value, approximately 246 giga-electronvolts. This spontaneous symmetry breaking differentiated the electromagnetic force, mediated by the massless photon, from the weak force, mediated by the now massive W and Z bosons. Through the Higgs mechanism, particles interacting with the Higgs field gained mass in proportion to their coupling strength. This monumental shift from symmetry to asymmetry shaped the character of matter. Electrons, quarks, and WZ bosons suddenly became massive, altering interaction rates and enabling the eventual formation of stable atoms. The electroweak phase transition also may have played a role in baryogenesis, depending on whether it was a smooth crossover or a first-order transition, a question still under investigation. In the vast chronology of cosmic history, this moment imprinted the diverse mass spectrum that underlies every chemical element and biological molecule. Quark Epoch. In the first microseconds after electroweak symmetry breaking, the universe was a roiling sea of fundamental constituents, 6 flavors of quarks and their gluon, glue. Temperatures soared to trillions of kelvins, and energy densities were so extreme that quarks refused confinement, darting freely through space in a deconfined state. Quantum chromodynamics, QCD, tells us that under these conditions, chiral symmetry is restored, rendering quarks effectively massless and radically altering their interaction rates. This era laid the groundwork for every proton and neutron that would later form. The very identity of particle was fluid, with quark-antiquark pairs constantly created and annihilated in a frenetic quantum dance. As the universe expanded, its cooling rate was governed by the rapid drop in relativistic degrees of freedom. Each species of quark and gluon contributed to the pressure and energy density in the Friedmann equations. Small asymmetries in CP-violating quark interactions may have already begun to tip the scales in favor of matter over antimatter, seeding the eventual baryon excess. Today, we recreate tiny droplets of this primordial plasma in heavy ion colliders, measuring quantities like shear viscosity to entropy density, which mirror the near-perfect fluidity of the early universe. By probing these transport coefficients, we glimpse how effectively the universe thermalized and how swiftly it transitioned toward the next great cosmic milestone: quark-gluon plasma. The quark-gluon plasma, QGP, era represents a state of matter so extreme that it can only be mimicked in the world's most powerful accelerators. In this epoch, quarks and gluons were not confined within hadrons but existed in a collective, nearly perfect fluid with remarkably low viscosity. Pressure waves, akin to sound, propagated through this plasma, and tiny anisotropies in these waves have been detected in collision experiments as elliptic flow, allowing physicists to reconstruct the QGP's equation of state. This relationship between pressure and energy density governed how rapidly the cosmos cooled and directly influenced the timing of confinement. Thermalization occurred on timescales of mere fractions of a yoctosecond, 10 to the negative 24 power seconds, ensuring the plasma maintained local thermodynamic equilibrium despite its rapid expansion. As the universe cooled below the critical temperature approximately 150 to 200 million electron volts, the QGP underwent a smooth crossover transition into a hadronic gas rather than abrupt first-order phase change. Modern measurements of jet quenching, how high-energy partons lose energy traversing the QGP, refine our understanding of color opacity and energy transport in the early universe. In essence, this era was the crucible in which quarks learned the art of confinement, setting the stage for the emergence of the familiar protons and neutrons that would later seed atoms. Hadron Epoch. When the temperature dipped below the QCD critical threshold, quarks and gluons could no longer outrun the strong force's binding potential. They coalesced into a zoo of hadronic states: mesons, quark-antiquark pairs, and baryons, three-quark triplets, but above all, into the stable protons and neutrons we recognize today. This hadronization was a smooth crossover, with different regions of the cosmos converting at slightly different times, yet without the release of latent heat characteristic of a first-order transition. The kinetics of this process involved gluon fragmentation into quark pairs and quark coalescence based on spatial proximity in phase space, forging the first heavy building blocks of matter. The effective relativistic particle count plummeted as hadrons replaced the deconfined quarks and gluons, accelerating the universe's cooling via the Friedmann expansion. In parallel, CP-violating interactions ensured that a tiny fraction of these protons and neutrons, about 1 in a billion pairs, survived annihilation, securing the cosmic matter excess. The precise yield of each Hadron species, predicted by thermal models calibrated against collider experiments, determined the initial conditions for Big Bang nucleosynthesis. Thus, the Hadron Epoch not only marked a change in the universe's particle roster, but dynamically reshaped its expansion history and chemical potential landscape. Dominance of hadrons. As hadrons solidified their presence, protons and neutrons became the dominant matter species within the primordial soup, yet their abundance was delicately balanced against their antimatter counterparts. Only when the temperature fell to around 20 to 30 million electron volts did the annihilation rates of proton-antiproton pairs drop below the Hubble expansion rate, leading to a freeze-out of the baryon number. Solving gamma, approximately H for this regime, yields the residual baryon to photon ratio of approximately 6 times 10 to the negative 10th, a cornerstone measurement gleaned from cosmic microwave background observations. This tiny leftover population of baryons would form the very atoms that later clumped into stars, galaxies, and planets. During this hadron-dominated phase, the surviving protons and neutrons coexisted with a dense radiation field of photons, electrons, positrons, and neutrinos. Their decoupling from annihilation meant they simply cooled with the expansion, no longer engaging in mass-altering processes. This irrevocable commitment to matter laid the foundation for the next critical chapters. The Lepton Epoch would shift the spotlight to lighter particles, and ultimately, the alchemy of Big Bang nucleosynthesis would transmute these hadrons into the universe's first atomic nuclei. Lepton Epoch. With hadrons securely confined, lighter leptons, electrons, positrons, muons, and their antiparticles dominated the energy density between 1 and 10 seconds after the Big Bang. Temperatures near 1 million electron volts fostered rapid pair creation and annihilation reactions, gamma plus gamma equals E plus E minus, sustaining thermal equilibrium. As the universe expanded and cooled, electron-positron annihilation began to outpace creation, injecting vast entropy into the photon bath. This entropy injection left photons slightly hotter than neutrinos, a subtle imbalance that sets today's temperature ratio T sub N over T sub G approximately equals 4/11 to the power of 3. Muons, heavier cousins of electrons, decayed on microsecond timescales into electrons and neutrinos, further enriching the cosmic neutrino background. These decays and annihilations influenced the chemical potentials and energy spectra of each species, fine-tuning conditions for the impending nucleosynthesis era. Although ephemeral, the Lepton Epoch's dynamics crucially impacted the distribution of entropy and energy among the universe's constituents, thereby dictating the precise thermal history that underpins both the cosmic microwave background's anisotropies and the abundances of light elements. Neutrino decoupling. At roughly 1 second after the Big Bang, neutrinos, interacting solely via the weak force, reached a point where their interaction rate gamma nu is approximately gf squared t to the 5th power, fell behind the Hubble expansion rate h. This decoupling at Td, approximately 1 to 2 million electron volts, liberated neutrinos from the plasma, letting them free stream through space almost unimpeded ever since. The resulting cosmic neutrino background, CNB, has cooled to approximately 1.95 Kelvin today, with an expected number density of about 340 neutrinos per cubic centimeter, an ancient echo of the universe's earliest moments. Though direct detection of the CMB remains a formidable experimental challenge, its influence is imprinted in the effective number of relativistic species, NDLF approximately 3.046, as inferred from the CMB power spectrum and large-scale structure. Furthermore, the free-streaming behavior of neutrinos suppressed growth of density perturbations below their characteristic free-streaming length, subtly shaping the pattern of galaxies and clusters we observe. In this sense, neutrino decoupling bridged the microphysics of weak interactions with the grand architecture of cosmic structure. Big Bang Nucleosynthesis. As the universe cooled to around 0.1 million electron volts, approximately 10 to the power of 9 Kelvin, the stage was set for the first nuclear reactions. Protons and neutrons collided via P plus N to D plus gamma, followed by a chain of fusion steps that built up helium-4, deuterium, and trace lithium-7. The interplay between reaction cross-sections, the neutron lifetime approximately 880 seconds, and the declining density determined the rates and yields of each species. Over the next few minutes, these processes forged the primordial abundances. Approximately 75% hydrogen-1 and approximately 25% helium-4 by mass, with minute fractions of deuterium, approximately 10 to the power of -5, and 371 helium-3 lithium-7, approximately 10 to the -10th power. Big Bang Nucleosynthesis, BBN, is a triumph of predictive cosmology. Observations of metal-poor gas clouds and ancient stars match BBN's forecasts to remarkable precision, constraining the baryon-to-photon ratio and ruling out many hypothetical particles or interactions that would alter light element yields. Small deviations, such as the persistent lithium problem, hint at either astrophysical processes that deplete surface lithium in stars or physics beyond the standard model. Nonetheless, BBN remains our best window into the universe's first minutes, cementing the connection between microphysics and cosmic evolution. Helium production. Helium-4's preeminence among the synthesized nuclei arises from its high binding energy, approximately 28 megaelectronvolts, and the abundance of its reactants. Once deuterium survived photodissociation, a rapid fusion chain drove nearly every available neutron into helium-4. The resultant helium mass fraction, Yp approximately equals 0.246, stands as one of cosmology's most robust predictions, confirmed by spectroscopy of low metallicity H2 regions in distant galaxies. Beyond its role as a primordial end product, helium-4 influenced the cooling of the first gas clouds. Its presence altered radiative cooling rates, affecting the collapse efficiency of population 3 star-forming regions. Without helium's unique thermal properties, the mass distribution and lifespan of the first stars, and thus the timeline of early reionization and heavy element enrichment, would have been markedly different. In this way, helium both reflects the universe's beginning and shapes its subsequent evolution. Lithium traces. Lithium-7's genesis is a delicate tale. Produced via the decay of beryllium-7, and to a lesser extent directly, its final abundance is exquisitely sensitive to nuclear reaction rates and the neutron-to-proton ratio. Standard BBN predicts a lithium-7 fraction, roughly 3 to 4 times higher than what we observe in the atmospheres of the oldest, most metal-poor stars, a discrepancy known as the Lithium Problem. Potential resolutions range from astrophysical depletion, surface mixing in stars that drags lithium into hotter layers where it is destroyed, to exotic physics like decaying supersymmetric particles altering the early neutron balance. Lithium-6, even rarer and more fragile, may also hold a primordial component, though cosmic ray spallation contributes significantly post-BBN. Precise measurements of both isotopes provide rigorous tests of nuclear astrophysics and early universe conditions. Solving the lithium conundrum could illuminate new facets of particle physics or stellar processes, making this humble element a powerful probe of the cosmos's first few minutes. End of nucleosynthesis. By 20 minutes after the Big Bang, the cosmic temperature had fallen below approximately 0.03 million electron volts, halting all significant nuclear reactions. The elemental composition, predominantly hydrogen and helium, with trace deuterium and lithium, became fixed, and nuclei ceased fusing. From this point forward, atomic abundances merely diluted with expansion, preserving a snapshot of nuclear alchemy at its dawn. This freeze-out transitioned the universe into the photon-dominated epoch, wherein radiation, photons and neutrinos governed dynamics until matter overtook radiation much later. The relics of BBN endure today not only in elemental ratios, but also in subtle spectral distortions of the cosmic microwave background and in the chemical fingerprints of ancient stars. Thus, the end of nucleosynthesis marks both a conclusion and an announcement. The universe, now seeded with the raw ingredients of chemistry, was ready to embark on its next grand adventure into structure formation and cosmic complexity. Photon Epoch. In the epoch following Big Bang nucleosynthesis, the universe was dominated by an opaque plasma of photons, electrons, and nuclei. Photons scattered relentlessly off free electrons via Thomson's scattering, rendering the cosmos a dense, glowing fog. Each photon's journey was akin to a pinball bouncing indefinitely, unable to travel more than microscopic distances before being deflected. This relentless interaction maintained thermal equilibrium. The radiation and matter shared a common temperature, and tiny density fluctuations were smoothed by the pressure of the photon baryon fluid. In this crucible, sound waves of compression and rarefaction, acoustic oscillations, rippled through the plasma, encoding the initial conditions that would later blossom into galaxies and voids. As expansion cooled the plasma, the mean free path of photons remained vanishingly small until the universe reached the threshold of recombination. Yet even in this opaque sea, primordial information was being written into subtle temperature and density variations. The tight coupling of photons and baryons generated a rich interplay. Gravity sought to collapse over densities, while radiation pressure pushed back, carving harmonious oscillations into the structure of the cosmos. These acoustic signatures would later appear as distinct peaks in the power spectrum of the cosmic microwave background, serving as a cosmic fingerprint of the photon epoch's dynamic dance. Matter-radiation equality. Roughly 47,000 years after the Big Bang, the energy densities of matter and radiation reached parity. Before this moment, radiation, relativistic particles including photons and neutrinos, held sway, its energy density decreasing as to the -4th power with the scale factor A. Matter's energy density, by contrast, fell as a -3A to the -3 a -3, since non-relativistic particles simply diluted with expansion. When these two components balanced, the dynamics of cosmic growth shifted dramatically. Gravity's ability to amplify density perturbations strengthened once matter dominated, unlocking the path toward large-scale structure formation. This critical juncture marked the end of radiation's suppressive grip on fluctuations. Post-equality dark matter could collapse unhindered into potential wells, dragging baryons along once they decoupled from photons. The scale at which equality occurred, set by the total matter density, imprinted itself on the horizon at that epoch, influencing the characteristic size of the first galactic seeds. In this sense, matter radiation equality was the universe's tipping point, where inertia overcame pressure and the blueprint for cosmic architecture began to take shape. Recombination. At around 380,000 years old, the universe's temperature fell to approximately 3,000 Kelvin, low enough for protons and electrons to combine into neutral hydrogen atoms in a process called recombination. Freed from their ionized partners, electrons bound to nuclei, and the plasma transitioned to a neutral gas. This dramatic shift reduced the universe's opacity. Photons could now travel vast distances without incessant scattering. Recombination was not instantaneous. It spanned tens of thousands of years as the balance between ionization and recombination delicately tipped, but its cumulative effect was profound, rendering space transparent for the first time. The recombination era also marked a pivotal cooling mechanism. As electrons bound to hydrogen, they released energy via Lyman series photons and two-photon processes, temporarily heating local regions before those photons redshifted into oblivion. The newly minted neutral gas began to cool adiabatically with expansion, setting the stage for the temperature contrast between gas and radiation that would drive later structure formation. In effect, recombination liberated light itself, ending the long photon epoch and ushering in the age where the cosmic microwave background could stream freely. Cosmic microwave background release. When photons decoupled at recombination, they formed the cosmic microwave background, CMB, a relic radiation bath that permeates the universe today. Initially peaking in the visible or infrared, cosmic expansion redshifted these photons into the microwave band, centering around 160 GHz. The CMB carries a nearly perfect blackbody spectrum, its uniformity to 1 part in 100,000 across the sky a testament to the homogenizing power of the early universe and its tiny anisotropies, the seeds of all cosmic structure. Observationally, the CMB's release was a cosmic flashbulb moment, a snapshot of the universe frozen at that precious instant. Satellites like COBE, WMAP, and Planck have since mapped the CMB's minute temperature fluctuations, revealing the scale and amplitude of primordial density variations. These fluctuations trace the acoustic oscillations of the photon baryon fluid and encode fundamental cosmological parameters such as the curvature, matter content, and expansion rate. In every pixel of the CMB sky lies a whisper of the universe's formative heartbeat. CMB temperature at decoupling. At the surface of last scattering, when photons last interacted significantly with matter, the temperature was about 3,000 Kelvin. This temperature determined the characteristic energy of photons and controlled the balance between ionized and neutral states of hydrogen. It set the ionization fraction curve, determining how rapidly recombination proceeded and how sharp the transition to transparency would be. Tiny variations in this temperature across space reflected underlying density perturbations and velocity flows at that cosmic moment. As the universe expanded by a factor of roughly 1100 since decoupling, that 3,000 Kelvin glow cooled to the 2.725 Kelvin we observe today. The precise measurement of this redshifted temperature is a triumph of observational cosmology, linking theory and observation across eons. It also serves as a cosmic thermometer. Any deviations in this value across the sky or with frequency would hint at new physics, yet the CMB remains the most perfect blackbody known, affirming our understanding of thermal processes at recombination. dark ages. Following decoupling, the universe entered a prolonged dark ages lasting hundreds of millions of years. With no luminous sources, yet before the ignition of the first stars, space was bathed only in the fading afterglow of the CMB and the radio whispers of atomic hydrogen's 21-centimeter transition. Gas cooled adiabatically, gradually losing the thermal energy it had inherited from recombination. Gravity, however, continued its inexorable work, amplifying tiny overdensities carved by acoustic waves and the imprint of dark matter's gravitational wells. During this era, baryons fell gently into dark matter potential wells, but without heat sources, they remained too diffuse to emit detectable light. Yet this silent epoch was far from quiescent. It was the incubator for the first luminous structures. The cooling and collapse of gas into ever denser clumps prepared the cosmic canvas for the dramatic appearance of the first stars and galaxies. Though unseen by optical telescopes, the Dark Ages hold the key to understanding how simplicity gave way to complexity. Gas clumping. As the Dark Ages unfolded, gravity bound gas into the invisible scaffolding laid down by dark matter. Tiny primordial density ripples, overdensities a fraction of a percent stronger than their surroundings, grew, drawing gas inward. Initially, thermal pressure counteracted collapse, but as cooling processes, notably hydrogen's molecular cooling via H2 formation, became efficient in denser regions, gas temperatures dropped, reducing pressure support. These conditions allowed gas to pool into ever more concentrated pockets, achieving densities where local self-gravity dominated. The clumping of gas was a hierarchical process. Small-scale density peaks collapsed first, merging into larger structures over time. These mini-halos, with masses around 10 to the power of 5 to 10 to the power of 6 mc, served as the cradle for the first stars. Their formation set a pace, bottom-up or hierarchical growth, where low-mass objects coalesced into more massive protogalaxies. The characteristics of gas clumping, its rate, spatial distribution, and thermal history, determined the timing and properties of proto-stellar nurseries, imprinting initial conditions for reionization and chemical enrichment. First stars, population 3. Roughly 100 million years after the Big Bang, the densest gas clumps in early mini-halos reached the critical threshold for hydrogen fusion, birthing the universe's first generation of stars, population 3. These stars, forged from pristine, metal-free gas, are believed to have been extraordinarily massive, perhaps tens to hundreds of times the mass of our Sun. Without heavier elements to facilitate cooling, the collapsing gas cores remained warmer, favoring the formation of colossal stars whose intense ultraviolet radiation would later carve ionized bubbles in the neutral medium. Population 3 stars lived fast and died young, their lifespans measured in mere millions of years. Their supernova explosions dispersed the first heavy elements into their surroundings, triggering a cascade of chemical and thermal feedback that would alter subsequent star formation. Moreover, their radiative output initiated the patchy reionization of the intergalactic medium, sowing the seeds of cosmic dawn. Although none of these primordial titans survive today, their legacy endures in the elemental fingerprints found in ancient metal-poor stars and in the large-scale ionization history of the universe. Early heavy elements. The explosive deaths of population 3 stars spewed the universe's first heavy nuclei, carbon, oxygen, silicon, and beyond, into the interstellar medium. These metals provided efficient cooling channels via atomic fine structure transitions, allowing gas in nascent protogalaxies to fragment into lower mass cores and give rise to population 2 stars with more familiar mass distributions. This chemical enrichment marked the universe's transition from simplicity to diversity as the periodic table began to fill out under stellar alchemy. These early enrichment events also influenced the opacity and thermodynamics of the intergalactic medium. Metal line cooling accelerated the collapse of gas in larger halos, catalyzing the formation of the first dwarf galaxies. Observations of high redshift quasar absorption spectra reveal metal absorption lines, indicating that heavy elements had already been dispersed over vast cosmic distances by redshift 6 to 7. Thus, the first supernovae acted not only as forgers of elements, but as cosmic dispersal agents, weaving metals into the tapestry of space long before our own Milky Way took shape. Protogalaxy Formation. As dark matter halos grew to masses of 10 to the power of 8 to 10 to the power of 9 m, they gathered enough gas to form protogalaxies, precursors to today's galaxies. Within these halos, gas could cool via atomic hydrogen line emission, settling into rotationally supported disks or turbulent clumps. Star formation rates accelerated. Feedback from supernovae and young stars drove winds that regulated further collapse, and merging of halos stitched together larger structures. These processes laid down the foundations of galactic morphology, bulges, disks, and early stellar halos. Protogalaxy formation was a symphony of competing forces: gravity's pull versus feedback's push, cooling's encouragement versus heating's restraint. Yet from this dynamic interplay emerged the first coherent galactic structures, building blocks that would merge and accrete to form the grand galaxies we see today. Tracing protogalaxies through observations of faint, high redshift dropout galaxies and Lyman-a emitters offers a glimpse into this formative chapter, revealing how the primordial universe blossomed into the richly structured cosmos we inhabit. Reionization Onset. About 150 million years after the Big Bang, the first luminous sources ignited and began to pierce the cosmic dark. These were predominantly massive, metal-free population 3 stars and the earliest protogalaxies, whose intense ultraviolet radiation ionized the surrounding hydrogen. As each star erupted into life, it carved out a spherical bubble of ionized gas, an H2 region within the otherwise neutral intergalactic medium, IgM. These bubbles expanded, overlapped, and eventually percolated, driven not only by stellar ultraviolet photons, but also by high-energy X-rays from early black hole accretion and supernova-driven shocks. The topology of reionization was highly inhomogeneous, with densely clustered regions around the first galaxies reionizing sooner, while vast voids remained shrouded in neutrality. This patchwork of ionized and neutral regions set the thermal history of the IgM, heating it to temperatures of 10 to the 4th to 10 to the 5th Kelvin, and altering its cooling and collapse behavior. Radiative feedback from these ionizing sources suppressed gas accretion onto low-mass dark matter halos by raising the gene's mass, stunting further star formation in the smallest potential wells. At the same time, chemical feedback, metals expelled by the first supernovae, polluted the surrounding gas, enabling new cooling channels for subsequent generations of stars. Observationally, the onset of reionization imprints a characteristic signal in the CMB's large-scale polarization through the Thomson scattering optical depth, while forthcoming 21-centimeter experiments aim to map the three-dimensional progress of these ionized bubbles. Reionization Completion. By around 1 billion years after the Big Bang, redshift Z approximately 6, deep surveys of distant quasars reveal the disappearance of the Gunn-Peterson trough, a signature of pervasive neutral hydrogen absorption, indicating that reionization had reached completion. At this stage, the ionized bubbles carved by successive generations of galaxies and quasars had finally overlapped, sufficiently to render the IgM nearly fully ionized. The final stages of this transition were driven by the cumulative photon budget from both star-forming galaxies and active galactic nuclei, with faint, numerous dwarf galaxies likely contributing the bulk of ionizing photons. The resulting ionization front velocities and the heat input set the residual temperature and clumping factor of the IgM, influencing future structure formation. This global phase change in the universe's transparency fundamentally reshaped galaxy formation. Low-mass halos below a critical threshold, approximately 10 to the power of 8 solar masses, were photoevaporated or prevented from accreting fresh gas, altering the faint end slope of the galaxy luminosity function. Pockets of self-shielded dense neutral gas survived longer, giving rise to damped Lyman alpha systems observed in quasar spectra long after the bulk of hydrogen was ionized. The end of reionization thus left a lasting imprint on the thermal and ionization state of the cosmos, with relic signatures detectable in the temperature-density relation of the IgM and in the small-scale power spectrum of the Lyman-a Forest. Cosmic web emergence. As dark matter density fluctuations grew under gravity's relentless pull, they evolved into a vast network of filaments, sheets, and nodes known as the cosmic web. This structure formation is elegantly captured by the Zeldovich approximation. Matter first collapses along one axis to form sheets, then along a second axis to form filaments, and finally along all three to form nodes or halos. High-resolution N-body simulations visualize this web spanning hundreds of millions of light-years, with massive clusters at the intersections and vast, underdense voids in between. The web's intricate geometry channels both dark matter and baryonic gas into narrow filaments, concentrating material where galaxy clusters and superclusters eventually emerge. Baryonic gas, following the dark matter skeleton, streams along these filaments and shocks as it accretes into halos, heating to the warm-hot intergalactic medium, WIM phase, at temperatures of 10 to the power of 5 to 10 to the power of 7 Kelvin. Observationally, the cosmic web is traced through galaxy redshift surveys, where galaxies outline filaments, and via the Lyman-a Forest in distant quasar spectra, which probes neutral hydrogen absorption along the line of sight. Emerging techniques in 21-centimeter tomography aim to directly image the web's evolution during reionization, promising a three-dimensional map of this grand design that underlies all cosmic structure. Dark matter scaffolding. Though invisible, dark matter constitutes roughly 27% of the universe's energy budget and provides the gravitational framework upon which all luminous structure is built. Tiny quantum fluctuations stretched during inflation seeded density perturbations in this collisionless component, which later grew into bound halos through hierarchical merging. Analytical models such as Press-Schechter theory predict the abundance of halos of different masses over time, while high-resolution simulations reveal detailed halo properties, including their Navarro-Frank-White, NFW density profiles, and concentration mass relations. These halos act as gravitational wells that pull in baryonic gas, dictating where and when galaxies can form. Within each dark matter halo, gas cools via atomic and molecular processes, losing pressure support and sinking toward the center to ignite star formation. The depth of the potential well governs the virial temperature and cooling efficiency. Massive halos retain hot gas that radiatively cools over longer timescales, while smaller halos may experience rapid cooling or even photoevaporation during reionization. Dark matter scaffolding thus not only sets the stage for galaxy formation, but also regulates feedback processes, supernova-driven outflows, and AGN jets that can expel baryons, temporarily quenching star formation and enriching the circumgalactic medium. Proto-Milky Way formation. Between 1 and 2 billion years after the Big Bang, multiple dark matter halos of 10 to the power of 9 to 10 to the power of 11 solar masses merged and accreted gas to form the Proto-Milky Way's first stellar populations. In these turbulent early mergers, rotating gas disks began to settle as angular momentum redistributed, giving rise to a primordial disk structure. Bursts of star formation ensued, enriched by the first Type II supernovae that injected heavier elements into the surrounding medium. Meanwhile, dynamical friction drove smaller satellite galaxies inward, building up a stellar halo and thick disk through disrupted merger remnants. Archaeological evidence of this protogalactic phase comes from stellar kinematics and chemical abundances. Surveys such as Gaia have identified ancient stellar streams, remnants of accreted dwarfs, wrapping around the Milky Way, while high-resolution spectroscopy reveals variations in A-element enhancements that trace the star formation histories of these early building blocks. Together, these fossil records map the assembly history of our galaxy, illustrating a mosaic built from numerous smaller progenitors whose contributions shaped the Milky Way's mass, structure, and chemical evolution. Population 2 stars. Following the brief but intense lives of population 3 stars, gas clouds enriched with carbon, oxygen, and other metals cooled more efficiently via fine structure transitions. This cooling allowed the fragmentation of gas into lower mass cores, giving rise to population 2 stars with masses spanning from subsolar to a few solar masses. Unlike their metal-free predecessors, these stars could survive for billions of years, and many still shine today in the galactic halo and in globular clusters. Their metallicities, often between 10 to the power of -3 and 10 to the power of -1 Z Sun, provide a record of early nucleosynthesis and mixing processes in the interstellar medium. Studying extremely metal-poor population 2 stars, some with Phi over H less than -4, offers a window into the yields of the first supernovae and the nature of the initial mass function at early times. Abundance patterns of R-process and S-process elements in these stars constrain the sites of heavy element formation, whether in neutron star mergers or rare classes of supernovae. In this way, population 2 stars act as cosmic archaeologists, preserving in their atmospheres the chemical fingerprints of the universe's formative epochs and guiding our understanding of stellar and galactic evolution. Galaxy mergers. Galaxies grow both by in situ star formation and by merging with other systems. When two galaxies of comparable mass collide, dynamical friction drags their dark matter, halos, and stellar components together, while tidal forces stretch and distort their shapes, producing spectacular tidal tails and bridges. Gas clouds within the colliding disks experience shocks and compression, triggering intense bursts of star formation, starbursts that can exhaust gas reservoirs in tens of millions of years. These mergers often funnel gas toward galactic centers, fueling central starbursts and feeding supermassive black holes, which may shine as active galactic nuclei, AGN. Mergers also drive long-term morphological transformation. Repeated interactions can thicken stellar disks, build bulges, and ultimately produce elliptical galaxies. Meanwhile, minor mergers, where a massive galaxy accretes much smaller satellites, contribute stars to the stellar halo and can induce transient waves or bars in the disk. Observationally, deep imaging surveys reveal a high incidence of tidal features around galaxies, indicating that merging is an ongoing process even in the local universe. Over cosmic time, hierarchical merging has been a primary engine of galaxy assembly, sculpting the diversity of galaxy types we observe today. First, quasars. By redshift Z, approximately 7, less than 800 million years after the Big Bang, surveys using wide-field infrared telescopes uncovered quasars powered by supermassive black holes, SMBH, with masses up to 10 to the 9th solar masses. Growing such behemoths so rapidly challenges theoretical models, either seed black holes of 10 to the 4th to 10 to the 5th m, solar masses formed via direct collapse in pristine gas clouds, or smaller seeds from population 3 stellar remnants accreted at or above the Eddington limit, almost continuously. The intense ultraviolet and X-ray radiation from these accreting black holes contributed significantly to local reionization, carving out ionized proximity zones in the IGM. Spectroscopic analysis of these high redshift quasars reveals broad emission lines and metal-enriched broadline regions, indicating vigorous chemical enrichment within their host galaxies. Damping wing absorption signatures in their spectra probe the neutral fraction of the IGM, offering direct constraints on the tail end of reionization. The presence of massive dust-rich host galaxies around these quasars also suggests that rapid star formation and black hole growth occur hand in hand, pointing to a fundamental coevolution between galaxies and their central engines from the universe's infancy. Cosmic noon. Around 3 billion years after the Big Bang, Z, approximately 2, the universe reached a crescendo of star formation. The cosmic star formation rate density peaked, converting vast reservoirs of cold gas into new stars at rates 10 to 100 times higher than in the present day. Massive gas-rich galaxies, often heavily dust-obscured, shone brightly in the infrared and submillimeter, while ultraviolet-selected Lyman break galaxies traced vigorous star-forming populations. This epoch saw the assembly of the bulk of stellar mass in today's massive galaxies, with both secular disk growth and merger-driven bursts contributing to their buildup. Simultaneously, the quasar population peaked, with luminous active galactic nuclei powered by rapidly accreting supermassive black holes dominating the energetic output of galaxies. Feedback from supernova-driven winds and active galactic nucleus jets regulated star formation, expelling gas and heating the circumgalactic medium, thereby quenching further growth in massive systems. The interplay between gas inflows along cosmic filaments and these feedback processes set the conditions for galaxy morphology, stellar age distributions, and the emergence of the Hubble sequence. Cosmic noon thus represents the universe's most productive era, a dynamic balance of creation and regulation that defined the galaxy populations we observe today. Dark energy dominance. Approximately 5 billion years after the Big Bang, Z approximately 0.6, observations of distant-type Ia Supernovae revealed that the cosmic expansion was accelerating rather than slowing under gravity's pull. This discovery implied the existence of a pervasive component, dubbed dark energy, with negative pressure that drives accelerated expansion. In the framework of lambda CDM, dark energy is modeled as a cosmological constant, lambda, representing about 68% of the total energy density. Its repulsive effect stretches spacetime, causing distant galaxies to recede at ever-increasing speeds. The nature of dark energy remains one of the deepest mysteries in physics. Is it truly a cosmological constant, an intrinsic property of spacetime, or a dynamic field, quintessence, evolving over time? Measurements of the equation of state parameter W equals P divided by R, where P is pressure and R is energy density, aim to distinguish these possibilities. Current observations favor W approximately equal to -1, but allow for slight deviations. As dark energy dominance continues, the universe drifts toward a dark, dilute future. Galaxies beyond our local group will recede beyond the cosmic event horizon, and the observable universe will shrink to an island of bound structures surrounded by expanding void. Solar system formation. Roughly 4.6 billion years ago, within a cold, rotating molecular cloud in the Milky Way's spiral arm, a dense clump began to collapse under its own gravity. As it contracted, conservation of angular momentum spun the cloud into a flattened protoplanetary disk surrounding a central protostar. Within this disk, dust grains and ices stuck together through electrostatic and collisional processes, gradually growing into kilometer-scale planetesimals. Over millions of years, these planetesimals accreted material through runaway and oligarchic growth, giving rise to the terrestrial planets in the inner disk and the massive gas giants further out, where icy solids could capture thick envelopes of hydrogen and helium. The sun ignited at the disk's center as temperatures and pressures became sufficient for hydrogen fusion, driving a powerful solar wind that swept away remaining gas and dust. This clearing defined the final architecture of our planetary system: rocky worlds within the asteroid belt, gas and ice giants beyond, and a haze of small bodies lingering in the Kuiper belt and Oort cloud. Water and organic compounds, delivered by cometary and asteroidal impacts, seeded Earth's surface, setting the stage for life. Today, the arrangement and composition of the solar system remain a living record of those formative processes. CMB, anisotropies, and structure seeding. When the cosmic microwave background, CMB, was released at recombination, it carried with it tiny temperature fluctuations, anisotropies at the level of 1 part in 100,000 that reflected the density ripples in the primordial plasma. These variations, imprinted by quantum fluctuations, magnified during inflation, delineated regions slightly denser or rarer than average. Over cosmic time, gravity amplified the overdense regions, causing matter to collapse into filaments and halos, while underdense voids expanded. Thus, the CMB anisotropies provided the initial blueprint for the universe's vast cosmic web of galaxies, clusters, and voids. Detailed mapping of these anisotropies reveals a rich tapestry of acoustic peaks and troughs in the angular power spectrum, each corresponding to oscillations in the photon baryon fluid before decoupling. The positions and amplitudes of these peaks encode fundamental cosmological parameters, such as the total matter density, baryon fraction, and curvature. By comparing theoretical models to observed anisotropy patterns, cosmologists have achieved unprecedented precision in reconstructing the universe's composition and geometry, firmly anchoring the lambda-cold dark matter (LCDM) paradigm, COBE, and the first CMB fluctuation detection. In 1992, NASA's Cosmic Background Explorer COBE satellite achieved the first measurement of temperature anisotropies in the CMB, detecting fluctuations of about 30 microkelvin against the 2.725 Kelvin blackbody. Prior to COBE, the CMB had been known as exquisitely smooth, but COBE's differential microwave radiometer unveiled the minute seeds of structure that inflationary theory predicted. This groundbreaking discovery transformed cosmology from a largely theoretical endeavor into a precision science, earning the 2006 Nobel Prize for John Mather and George Smoot. COBE's results also confirmed the CMB's nearly perfect blackbody spectrum, with distortions constrained to parts per 10 to the power of 5, validating the hot Big Bang model. The detection of anisotropies catalyzed a decade of technological development, leading to higher resolution missions. COBE set the stage for mapping these primordial ripples with finer, angular detail, establishing a legacy of cosmic microwave observations that would refine our understanding of dark matter, dark energy, and the universe's ultimate fate. WMAP's high-precision cosmic mapping. Between 2003 and 2010, the Wilkinson Microwave Anisotropy Probe WMAP delivered a full-sky map of CMB temperature and polarization anisotropies with tenfold improved resolution over COBE. WMAP measured fluctuations down to scales of about 0.2 degrees, pinpointing the positions and heights of the first 3 acoustic peaks with exquisite clarity. From these data, key parameters, including the Hubble constant, baryon density, and spectral index of primordial fluctuations, were determined to within a few percent, solidifying the lambda-CDM framework. Beyond temperature maps, WMAP's polarization measurements provided independent confirmation of the Reionization Epoch, suggesting that the first stars formed between redshifts Z, approximately 11 and 30. The consistency between temperature and polarization data reinforced our models of early universe physics, while minor tensions sparked investigations into additional physics, such as neutrino mass and cosmic defects. WMAP's legacy endures in the precision with which it framed modern cosmology and in the technological innovations it spurred for subsequent experiments. Planck mission and precision cosmology. Launched in 2009 by the European Space Agency, the Planck satellite mapped the CMB's temperature anisotropies down to angular scales of 5 arc-minutes and measured polarization with unprecedented sensitivity. Planck's all-sky survey refined estimates of cosmological parameters to sub-percent precision. The total energy density, O-tot, baryon and dark matter densities, O-B, O-C, and the scalar spectral index, NS. The mission further constrained the sum of neutrino masses and limited the tensor-to-scalar ratio, tightening bounds on inflationary models. Planck's polarization maps have also illuminated the history of reionization, indicating a somewhat later and more rapid transition than WMAP suggested. This adjustment harmonized CMB data with observations of high redshift galaxies and quasars, refining our timeline of early star and galaxy formation. Planck's high-fidelity measurements have become the gold standard for cosmology, anchoring countless theoretical and observational studies and guiding the design of next-generation microwave observatories. Cosmic energy budget, dark energy, dark matter, and baryons. Observations of the CMB, large-scale structure, and type Ia Supernovae converge on a cosmic composition of roughly 68% dark energy, 27% dark matter, and 5% ordinary baryonic matter. Dark energy, manifested as a cosmological constant or dynamic field, drives accelerated cosmic expansion. Dark matter, detectable only through gravity, provides the framework for galaxy formation. And baryons constitute the stars, gas, and dust visible in telescopes. This tripartite energy budget underpins the Lambda-CDM model, which successfully reproduces a diverse array of astronomical observations across 13.8 billion years. Despite its empirical success, the nature of dark energy and dark matter remains deeply mysterious. Particle physics experiments and astrophysical searches have yet to reveal dark matter candidates, while the cosmological constant's extraordinarily small value compared to theoretical expectations poses the vacuum catastrophe. These profound puzzles motivate ambitious observational campaigns, such as wide-area galaxy surveys and precision-weak lensing studies, and fundamental theory efforts, including modifications of gravity and searches for new particles, aiming to illuminate the dark sectors that dominate our universe. Hubble's law and cosmic expansion. In 1929, Edwin Hubble discovered that galaxies recede from us at speeds proportional to their distances, a relation expressed as v equals h0.d, where h0 is the Hubble constant. This empirical law revealed that space itself is expanding, carrying galaxies apart like dots on a stretching balloon. Hubble's original measurement of h0, approximately 500 kilometers per second per megaparsec, has been refined over decades to the modern value near 70 kilometers per second per megaparsec, anchoring the cosmic distance ladder and establishing the scale and age of the universe. Hubble's law is not merely a kinematic statement, but emerges from general relativity's description of an expanding spacetime. The metric for a homogeneous, isotropic universe, the Friedmann-Lemaitre-Robertson-Walker metric, predicts redshifting of light and growth of scale factor A of t. Observations of redshift distance relations across cosmic time probe the expansion history, revealing transitions from radiation to matter dominance, and from deceleration to dark energy-driven acceleration. Thus, Hubble's law remains central to cosmology, linking theory with observation. The Hubble Tension, a cosmological conundrum. In recent years, measurements of the Hubble constant using local distance indicators, CFED-calibrated supernovae, have yielded values near 73 to 74 kilometers per second per megaparsec, while early universe inferences from Planck's CMB data favor H0 approximately 67 to 68 kilometers per second per megaparsec. This discrepancy, now exceeding 4 sigma significance, has become known as the Hubble tension. If systematic errors are ruled out, the tension may signal new physics beyond lambda-CDM, such as early dark energy, modifications to neutrino properties, or interactions within the dark sector. Resolving the Hubble tension is a major focus of modern cosmology. Independent measurements using strong gravitational lensing time delays, baryon acoustic oscillations with distance anchors, and gravitational wave standard sirens are beginning to weigh in, some favoring high H0, others low, and still others intermediate. The eventual convergence or sustained divergence of these methods will illuminate whether we face a calibration challenge or the dawn of new fundamental insights into the universe's expansion history. Baryon acoustic oscillations as standard rulers. Before recombination, sound waves rippled through the photon baryon plasma at roughly half the speed of light, driven by the interplay of radiation pressure and gravity. These baryon acoustic oscillations, BAO, left a characteristic scale, about 150 megaparsecs today, in the clustering of galaxies, an excess probability to find pairs separated by this distance. Galaxy redshift surveys such as SDSS, 2DFGRS, and DESI measure this BAO feature in the galaxy two-point correlation function, providing a standard ruler for tracing the universe's expansion at different epochs. By comparing the observed BAO scale to theoretical predictions, cosmologists infer angular diameter distances and Hubble parameters across redshift, mapping the cosmic expansion history independently of supernovae. BAO measurements tightly constrain the matter density and dark energy equation of state parameter, complementing CMB and weak lensing data. Future surveys aim to chart BAO in the distribution of neutral hydrogen via 21 centimeter intensity mapping, promising three-dimensional maps of cosmic expansion from the dark ages through cosmic noon. Consistency of light element abundances with Big Bang predictions. Big Bang Nucleosynthesis, BBN theory, predicts primordial abundances of hydrogen, helium-4, deuterium, and lithium-7 based on the baryon to photon ratio. Observations of deuterium in high redshift quasar absorption systems and helium in metal-poor extragalactic H2 regions agree with BBN predictions to better than 1%, providing a key pillar of the hot Big Bang model. The relative concordance of these light element abundances with CMB inferred baryon densities offers a cross-epoch consistency check spanning minutes to 380,000 years after the Big Bang. The only notable exception is lithium-7, whose observed abundance in ancient stellar atmospheres is 2 to 4 times lower than BBN forecasts, a discrepancy dubbed the Lithium Problem. Proposed solutions include stellar depletion mechanisms, nuclear reaction rate uncertainties, or physics beyond the standard model, such as decaying particles altering neutron to proton ratios. Resolving this anomaly remains an active research frontier, as it could reveal new insights into early universe conditions or stellar physics. Horizon Problem. In the standard Big Bang framework without inflation, regions of the universe separated by more than about 1 degree on the sky, corresponding to roughly 100,000 light-years at the time of last scattering, should never have been in causal contact. Light signals couldn't traverse the intervening distance before recombination. Yet observations of the cosmic microwave background, CMB, reveal a remarkable uniformity in temperature across the entire sky to 1 part in 100,000. This astonishing isotropy poses the horizon problem. How did these vast, causally disconnected regions know to come into thermal equilibrium and share the same temperature? Traditional physics, without an additional mechanism, simply cannot account for the observed homogeneity. Beyond being a technical curiosity, the horizon problem strikes at the heart of our understanding of cosmic origins. It suggests a deeper coherence in the infant universe, one that ordinary expansion could not establish in the brief 380,000 years before recombination. The uniformity of the CMB implies that at some point, the entire observable universe must have been contained within a much smaller, causally connected region, an idea that challenged cosmologists to rethink the very nature of space and time at the universe's birth. It is this puzzle that inflationary theory so elegantly resolves, but the horizon problem itself remains a powerful reminder that the cosmos harbors mysteries beyond simple extrapolation. Flatness Problem. General relativity allows for universes with positive, negative, or zero spatial curvature, corresponding to closed, open, or flat geometries. Observationally, the universe today appears extraordinarily flat. Its curvature parameter, omega total, differs from unity by less than 1 part in 100. In the absence of a special mechanism, any tiny deviation from perfect flatness in the early universe would have been amplified over time, driving the cosmos toward either rapid recollapse, if closed, or runaway expansion, if open. The fact that we find ourselves in a universe so finely balanced at critical density demands an initial curvature set to within 1 part in 10 to the power of 55 at the Planck time, a level of fine-tuning that cries out for explanation. This flatness problem underscores a profound tension in cosmology: how to naturally explain why the universe sits so precisely at the knife's edge between eventual collapse and eternal curvature-driven acceleration. Such extreme sensitivity to initial conditions seems unnatural, akin to balancing a pencil perfectly upright on its tip. Without a mechanism to dynamically drive curvature towards zero, the flatness we observe today would require an almost miraculous coincidence in the universe's earliest moments. Inflation again offers a compelling resolution, stretching any initial curvature to near flatness. But the flatness problem itself highlights how our cosmos carries the imprint of processes vastly more powerful than simple expansion. Monopole Problem. Grand unified theories, GUTS, predict that during the high-energy symmetry breaking in the early universe, topological defects such as magnetic monopoles should have formed in abundance. These hypothetical particles would carry a net magnetic charge, analogous to electric charge, and their mass would be on the order of the GUT scale, immensely heavy and long-lived. If they were produced copiously during the GUT phase transition, their residual density today would vastly exceed observational limits, dominating the mass-energy budget of the universe and contradicting the absence of any detected monopole events in experiments. The monopole problem is more than an idle theoretical concern. It illustrates how naively extrapolating high-energy physics to cosmology can lead to stark conflicts with reality. Given the lack of observed monopoles, something must intervene to suppress their abundance or dilute them to imperceptible levels. This challenge propelled the development of inflationary cosmology, wherein a brief epoch of exponential expansion could stretch space so dramatically that even a large initial monopole density would be diluted to effectively zero within our observable volume. Thus, the monopole problem, like the horizon and flatness issues, pointed toward new, radical ideas about the universe's earliest behavior. Inflation's solution to the classic problems. Inflationary theory posits that the universe underwent a phase of exponential expansion, driven by the potential energy of a scalar inflaton field. In a tiny fraction of a second, far less than 10 to the negative 32nd seconds, space expanded by a factor of at least 10 to the 26th in each spatial direction. This staggering growth outpaced the speed at which causal influences propagate, stretching tiny, causally connected regions to encompass the entire observable universe. Consequently, the horizon problem is resolved. All parts of our sky today share a common thermal history because they originated from a single small patch in causal contact before inflation. Simultaneously, inflation flattened any pre-existing curvature by diluting spatial deviations, solving the flatness problem in one fell swoop. The exponential growth also diluted the density of unwanted relics, such as magnetic monopoles or other heavy exotic particles, by many orders of magnitude, addressing the monopole problem. Through these three triumphs, inflation transforms what were once severe fine-tuning issues into natural outcomes of dynamical evolution. The theory's elegance lies in its ability to link quantum field dynamics at ultra-high energies with the large-scale uniformity and geometry we observe billions of years later. Quantum fluctuations stretched to cosmic scales. While inflation smoothed and flattened space-time, it simultaneously amplified quantum fluctuations, microscopic jitters in the inflaton field and metric, by stretching them beyond the Hubble horizon. In ordinary conditions, such fluctuations average out and remain confined to subatomic scales, but during inflation, the rapid expansion freezes these perturbations into classical density variations imprinted on the fabric of space. These frozen fluctuations thus became the primordial seeds from which all cosmic structure grew, an extraordinary bridge between the quantum realm and the macroscopic universe. These quantum fluctuations are statistical in nature, characterized by a nearly scale-invariant power spectrum, a hallmark prediction of inflation. Tiny differences in fluctuation amplitude yield temperature anisotropies in the CMB at the level of delta T by T approximately 10 to the minus 5, exactly as observed by experiments like COBE, WMAP, and Planck. The realization that quantum uncertainty could spawn galaxies, galaxy clusters, and the cosmic web lends a profound poetic dimension to cosmology. The same quantum fuzziness that limits our knowledge of a particle's position gave birth to the grandest structures in the universe: density perturbations and structure formation. After inflation ended, the universe transitioned into a hot, radiation-dominated phase, carrying with it the imprinted density perturbations. Regions slightly denser than average exerted greater gravitational pull, attracting surrounding matter and growing via the process of gravitational instability. Conversely, underdense regions became voids as matter flowed away. Over millions to billions of years, these initially tiny over- and underdensities evolved into the vast cosmic web, filaments of galaxies tracing the original peaks and voids reflecting the troughs in the primordial fluctuation spectrum. The linear growth of these perturbations during the radiation and early matter-dominated eras is well described by perturbation theory, while the later non-linear regime, where structures collapse to form halos, galaxies, and clusters, requires sophisticated numerical simulations. Observations of galaxy clustering, weak gravitational lensing, and the Lyman-a Forest all map this evolution, providing a potent cross-check of inflation's initial conditions. The concordance between theory and observation underscores how the universe's entire large-scale architecture is rooted in those earliest density ripples, quantum whispers magnified to cosmic grandeur. CMB E-Mode Polarization as acoustic conformation. Beyond temperature anisotropies, the CMB also exhibits polarization patterns arising from Thomson's scattering of anisotropic radiation off free electrons at recombination. These patterns split into even parity E-modes and odd parity B-modes. E-mode polarization was first detected by the Degree Angular Scale Interferometer, DASI, in 2002 and later mapped in exquisite detail by WMAP and Planck. The spatial correlation between temperature and E-mode patterns confirms the presence of acoustic oscillations in the photon baryon fluid, compressions and rarefactions driven by gravity and radiation pressure prior to decoupling. The amplitude and angular dependence of E-mode polarization offer independent measurements of key cosmological parameters. They refine estimates of the reionization optical depth, revealing when the first stars formed, and sharpen constraints on baryon and dark matter densities. Moreover, the precise agreement between the observed E-mode spectrum and theoretical predictions provides one of the strongest validations of the LCDM plus inflation paradigm, linking early universe physics with late-time cosmic structure. CMB B-Mode Searches for primordial gravitational waves. While E-modes arise from scalar density fluctuations, the elusive B-modes can be generated by tensor perturbations, primordial gravitational waves sourced during inflation. Detecting the B-mode signal on degree scales would provide a direct probe of inflation's energy scale, pinning down the inflaton potential and offering a glimpse of quantum gravity phenomena. Experiments such as BICEP, Keck, Polar Bear, and the South Pole Telescope have been tirelessly pushing down upper limits on the tensor-to-scalar ratio R, striving to separate the faint primordial whispers from foreground dust and lensing contamination. The challenge is formidable. The expected signal is millions of times fainter than the CMB's temperature anisotropies, and astrophysical foregrounds, polarized emission from the Milky Way's dust, and synchrotron radiation must be meticulously characterized and removed. Nonetheless, the potential payoff is enormous. A robust detection of primordial B-modes would not only confirm inflation, but also measure its energy scale, opening a rare window onto physics at grand unification or Planckian realms. It represents one of cosmology's most ambitious quests, uniting experimental ingenuity with theoretical ambition. Primordial gravitational waves and the quest for confirmation. Primordial gravitational waves, ripples in spacetime generated by quantum fluctuations of the inflaton field, are predicted by virtually all inflationary models. Their amplitude is set by the inflationary Hubble rate, Hinf, providing a direct measure of the energy density during that epoch. Beyond B-mode polarization, future probes include space-based laser interferometers, e.g. the Japanese Lightbird mission, and pulsar timing arrays, which aim to detect these ancient waves across a broad frequency spectrum. A positive signal would revolutionize our understanding of the very fabric of spacetime, confirming that gravity, like other forces, is subject to quantum uncertainty. Conversely, a stringent upper bound on primordial gravitational waves constrains inflationary scenarios, ruling out high-energy models and favoring lower-scale or multi-field frameworks. The absence of detection after successive generations of increasingly sensitive experiments could suggest alternative mechanisms for smoothing the early universe or point toward new physics suppressing tensor modes. In either case, the hunt for primordial gravitational waves stands at the frontier of cosmology, poised to illuminate or challenge our deepest theories of cosmic genesis, cosmic strings, and topological defects. In certain high-energy phase transitions, particularly those associated with grand unified theories, the universe might have formed one-dimensional topological defects known as cosmic strings. These hypothetical filaments would carry immense energy per unit length, producing gravitational signatures such as line discontinuities in the CMB temperature map, distinct patterns in gravitational lensing, or bursts of gravitational waves when loops oscillate and decay. While no definitive evidence has emerged, searches using the Planck, CMB data, and pulsar timing arrays have placed stringent upper limits on the string tension, GM less than or equal to 10 to the power of -7, effectively ruling out many simple defect scenarios. The study of cosmic strings continues to intrigue theorists, as they offer a unique link between particle physics and cosmology. If discovered, they would provide direct evidence of symmetry-breaking phenomena at energy scales far beyond terrestrial accelerators. Even null detections refine our understanding of high-energy physics and guide model building for the early universe. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, and advanced pulsar timing arrays, promise to push sensitivity further. ensuring that the cosmic string hypothesis remains an active and exciting frontier in the quest to decode the universe's primordial symmetries. Cosmic web. The cosmic web is the grand-scale network of matter that permeates the universe, woven from the primordial density fluctuations seeded during inflation. Dark matter, which interacts only gravitationally, collapsed first into an intricate scaffolding of filaments and nodes, leaving vast voids in between. Baryonic gas followed this dark backbone, flowing along filaments into gravitational wells, where it cooled and formed stars and galaxies. This filamentary structure spans hundreds of millions of light-years, with galaxy clusters residing at the intersections and thin bridges of matter, linking them. On smaller scales, the cosmic web's geometry influences galaxy evolution. Gas accretion along filaments can sustain star formation, while shocks at filament intersections heat gas into the warm, hot intergalactic medium, WIM. Observationally, we map the web through galaxy redshift surveys, tracing galaxy positions in 3 dimensions, and through absorption features such as the Lyman-a Forest in quasar spectra, which samples the diffuse gas between galaxies. Future 21-centimeter intensity mapping experiments aim to image the web during the dark ages, providing a direct view of structure emergence long before the first stars ignited. Galaxy clusters. Galaxy clusters are the universe's most massive gravitationally bound structures, containing hundreds to thousands of galaxies, vast reservoirs of hot intracluster gas, and a dominant dark matter component. The intracluster medium, ICM, reaches temperatures of 10 to the power of 7 to 10 to the power of 8 Kelvin, emitting copious X-rays that reveal the cluster's mass distribution and dynamical state. Clusters grow hierarchically. Smaller groups merge under gravity, generating shock waves and turbulence in the ICM, and occasionally igniting spectacular radio relics and halos observable at low radio frequencies. Beyond their role as cosmic laboratories for high-energy astrophysics, clusters serve as sensitive tracers of cosmological parameters. Their abundance and mass function over cosmic time depend critically on the matter density and the growth rate of structure, providing complementary constraints to the CMB and supernova measurements. Weak and strong gravitational lensing by clusters also map dark matter at high resolution, unveiling substructures and testing the collisionless nature of dark matter particles. Cosmic voids. Cosmic voids are immense, underdense regions that occupy most of the universe's volume, often spanning tens to hundreds of millions of light-years. Within these voids, matter density can be less than 20% of the cosmic mean, and the lack of structure makes them remarkable probes of cosmology. Void dynamics are sensitive to dark energy's repulsive effect and to modifications of gravity. Galaxies within voids often exhibit unique properties: lower masses, slower star formation rates, and more isolated evolution, offering insights into environmental effects on galaxy formation. Voids also imprint distinctive patterns on observables. The Alcock-Pazinski test applied to void shapes constrains the expansion history, while the integrated Sachs-Wolf effect leads to cold spots in the CMB, where photons traverse decaying gravitational potentials. Additionally, the low-density environment reduces non-linear gravitational interactions, making void regions cleaner laboratories for testing the initial conditions of the universe and for measuring the sum of neutrino masses through subtle shifts in void abundance and clustering. Sunyaev-Zeldovich Effect. The Sunyaev-Zeldovich effect arises when CMB photons scatter off high-energy electrons in hot cluster gas, gaining energy through inverse Compton scattering. This process imprints a distinctive spectral distortion on the CMB, a decrement in intensity at low frequencies and an increment at high frequencies relative to the primordial blackbody. Because the SZ signal depends on electron pressure integrated along the line of sight, it provides a nearly redshift-independent probe of cluster gas content, allowing us to detect clusters out to the far reaches of the observable universe. SZ surveys, conducted by instruments like the South Pole Telescope and the Atacama Cosmology Telescope, have catalogued thousands of clusters, complementing X-ray and optical observations. By combining SZ measurements with X-ray data, astronomers can disentangle gas temperature, density, and total mass, refining scaling relations that connect observable quantities to cluster masses. These calibrated mass estimates feed into cosmological analyses of cluster abundance and spatial clustering, tightening constraints on dark energy and the growth of cosmic structure. Lyman-a Forest. The Lyman-a Forest consists of a multitude of absorption lines, blue ward of the Lyman-a emission line in quasar spectra, produced by neutral hydrogen in the intergalactic medium, IgM. As light from a distant quasar traverses cosmic space, it encounters clouds and filaments of diffuse hydrogen gas, each imprinting an absorption line at the red-shifted wavelength corresponding to the cloud's velocity. The forest's line density, width, and clustering encode the IgM's temperature, density fluctuations, and ionization state during and after reionization. High-resolution spectrographs on large telescopes enable precise measurements of the Lyman-a Forest, transforming it into a three-dimensional map of matter on scales from megaparsecs down to kiloparsecs. Analyses of the forest's power spectrum constrain cosmological parameters, such as the matter-power spectrum amplitude and the spectral index, and probe the thermal history of the IgM. Moreover, cross-correlations between Lyman-a absorption and galaxy positions reveal how galaxies affect their surroundings, illuminating feedback processes that heat and enrich intergalactic gas. Cosmic neutrino background. The cosmic neutrino background, CMB, is the sea of relic neutrinos that decoupled roughly 1 second after the Big Bang, when the universe was at temperatures around 1 to 2 million electron volts. These neutrinos have since cooled to a temperature of about 1.95 Kelvin, slightly colder than the cosmic microwave background, and permeate space with an estimated density of approximately 340 cubic centimeters per cubic centimeter. Although their weak interactions make them extraordinarily difficult to detect directly, their collective gravitational effects influence cosmological observables, such as the expansion rate, CMB Anisotropies, and large-scale structure formation, allowing indirect inference of their properties. Future experiments aim to capture the CMB through neutrino capture on beta-decaying nuclei, e.g. tritium, in experiments like Ptolemy, which would observe a peak in the electron spectrum above the beta-decay endpoint. Even without direct detection, the CMB's contribution to the radiation energy density is constrained by measurements of the effective number of neutrino species. NNF is approximately 3.046. Tiny deviations from this value could signal additional relic particles or non-standard neutrino thermal histories, offering a window onto physics beyond the standard model. 21 centimeters cosmology. Observations of the 21-centimeter hyperfine transition of neutral hydrogen promise to revolutionize our view of the dark ages and cosmic dawn, mapping the intergalactic medium before and during the first luminous sources. In the absence of stars, the 21-centimeter signal depends on the gas temperature, density, and Lyman-alpha coupling, yielding a three-dimensional tomographic view of structure formation on scales from subgalactic to cosmological. Experiments like EDGES, LOFAR, and the upcoming Square Kilometre Array, SKA, seek to detect the global 21-centimeter signal and its spatial fluctuations, probing the timing of first star formation and the heating and ionization history of the early universe. 21 centimeters cosmology complements CMB and galaxy surveys by filling the observational gap between recombination and reionization. The vast volume accessible in 21-centimeter studies dramatically reduces cosmic variance and enables precise measurements of fundamental parameters, including the matter-power spectrum, dark energy equation of state, and possible non-Gaussianities in primordial fluctuations. Moreover, by tracking the imprint of astrophysical feedback on the IGM, 21-centimeter observations will illuminate the interplay between the first galaxies, black holes, and the diffuse gas that envelops them. LCDM Model. The lambda cold dark matter, lambda CDM model, is the prevailing cosmological paradigm, characterizing the universe's composition and evolution with just 6 key parameters: the Hubble constant, baryon density, dark matter density, amplitude and spectral index of primordial fluctuations, and the optical depth to reionization. In lambda CDM, dark energy, lambda, drives late-time acceleration, while cold dark matter, CDM, seeds structure formation through gravitational collapse. This simple framework successfully reproduces a wealth of observations, from the CMB angular power spectrum to galaxy clustering and the accelerating expansion revealed by Type Ia Supernovae. Despite its empirical triumphs, lambda CDM leaves fundamental questions unanswered. The physical nature of dark energy and dark matter remain unknown, and small-scale discrepancies, such as the Quark problem or satellite galaxy counts, challenge pure CDM predictions. Ongoing and planned surveys, e.g., DESI, Euclid, Roman Space Telescope, aim to test lambda CDM's assumptions with unprecedented precision, probing the possibility of dynamic dark energy, warm dark matter, or novel interactions that could refine or extend the standard model of cosmology. Modified gravity theories. Modified gravity theories propose alternatives to dark energy by altering Einstein's general relativity on cosmological scales, seeking to explain cosmic acceleration through new gravitational physics. Examples include FR gravity, in which the Ricci scalar in the Einstein-Hilbert action is replaced by a function FR, and scalar tensor theories like Brans-Dicker, which introduce additional scalar fields mediating gravity. These modifications can mimic an effective cosmological constant or lead to scale-dependent growth of structure, yielding testable differences in the expansion history and the behavior of gravitational potentials. Precision tests of gravity on astrophysical and cosmological scales, through galaxy cluster abundance, redshift space distortions, and weak gravitational lensing, constrain deviations from general relativity. Screening mechanisms, such as the chameleon or Weinstein effects, allow modified gravity to satisfy solar system tests while exhibiting novel behavior on large scales. The synergy of multiple probes across redshift and scale will either tighten the limits on modifications or uncover signatures that point toward a richer theory of gravity underlying the accelerating universe. Dark matter candidates. While dark matter's gravitational influence is incontrovertible, its particle identity remains one of physics' great enigmas. Weakly interacting massive particles, WIMPs, predicted by supersymmetric extensions of the Standard Model, have long been the leading candidate. Their predicted relic abundance naturally aligns with observations, WIMP miracle. Despite extensive searches in deep underground detectors, e.g. Xenon 1T, LUX, and indirect probes of annihilation signals, no conclusive WIMP signal has emerged, prompting exploration of alternative candidates. Axions, ultralight particles, arising from solutions to the strong CP problem, offer another compelling possibility. They could form a cold Bose-Einstein condensate and be detectable via resonant magnetic cavity experiments, e.g. ADMX. Sterile neutrinos, heavier cousins of Standard Model neutrinos that mix weakly with active neutrinos, could explain small-scale structure through their non-relativistic, warm behavior and might reveal themselves in X-ray decay lines. The breadth of dark matter candidate space now spans many orders of magnitude in mass and interaction strength, with experiments from tabletop searches to large-scale astrophysical surveys collectively narrowing the field in pursuit of the universe's missing mass. Direct dark matter searches. Deep underground laboratories around the world host experiments designed to catch the faintest interactions between dark matter particles and ordinary nuclei. Shielded by kilometers of rock from cosmic rays and environmental radioactivity, detectors such as Lux Zeppelin, Xenon T, and Panda X employ ultra-pure liquid noble gases, xenon or argon, as target materials. When a dark matter particle, often hypothesized as a weakly interacting massive particle, WIMP, collides with a nucleus in the detector, it imparts a tiny recoil energy that generates scintillation light and free electrons. These signals are measured with photomultiplier tubes and time projection chambers, allowing scientists to distinguish potential dark matter events from background noise through pulse shape discrimination and three-dimensional event localization. Despite decades of effort, no unambiguous dark matter signal has yet emerged, pushing experiments to ever lower cross-section sensitivities and prompting the development of novel technologies. Future detectors aim to increase target mass by orders of magnitude and improve background rejection through advanced material purification and veto systems. Parallel efforts explore alternative candidates, such as axions and hidden sector particles, using resonant cavities, superconducting sensors, and low-threshold cryogenic detectors. Each null result refines the parameter space of viable dark matter models, guiding theoretical work toward new mass ranges and interaction channels, and underscoring the interplay between experiment and theory in the quest to identify the universe's missing mass. Galaxy rotation curves. In the 1970s, pioneering work by Vera Rubin and Kent Ford revealed that the outer regions of spiral galaxies rotate much faster than can be accounted for by the visible distribution of stars and gas. By measuring the Doppler shifts of emission lines from hydrogen clouds at various radii, they found flat rotation curves. Orbital velocities remained roughly constant instead of declining with distance, as Newtonian gravity would predict for the observed baryonic mass. This discrepancy implied the presence of an unseen mass component, dark matter, extending well beyond the luminous disk and dominating the galaxy's gravitational potential. Subsequent studies across hundreds of galaxies confirmed this universal behavior, and detailed mass modeling enabled the reconstruction of dark matter halo profiles, such as the Navarro-Frank-White NFW profile, predicted by cold dark matter simulations. These profiles describe a central density cusp and an outer density that falls off as r to the power of -3, although observations of dwarf and low-surface brightness galaxies sometimes show shallower cores, sparking debates over feedback processes versus alternative dark matter properties. Galaxy rotation curves thus remain a cornerstone of dark matter evidence, linking galactic dynamics to cosmological structure formation. Gravitational lensing. Einstein's general relativity predicts that mass curves spacetime, bending the paths of light rays passing nearby. In gravitational lensing, massive objects, galaxies or galaxy clusters, act as lenses, distorting, magnifying, and sometimes producing multiple images of background sources. Weak lensing surveys measure the subtle, coherent stretching of galaxy shapes across vast regions of sky, statistically mapping the total matter distribution, both luminous and dark. This cosmic shear signal provides direct, model-independent measurements of the matter power spectrum and the growth of structure over cosmic time. Strong lensing, by contrast, creates dramatic arcs and Einstein rings when a background galaxy or quasar aligns closely behind a massive foreground lens. Detailed modeling of these configurations yields precise mass measurements of the lensing object, including the substructure of dark matter halos down to subgalactic scales. Combined with kinematic and X-ray data, lensing studies probe the nature of dark matter, constraining its self-interaction cross-section, and test gravity itself on scales unreachable by other methods. In this way, gravitational lensing transforms distant galaxies into cosmological laboratories. Type Ia Supernovae, an accelerated expansion. In the late 1990s, two independent teams studying type Ia Supernovae, standardizable candles caused by white dwarfs reaching a critical mass, found that distant explosions appeared dimmer than expected in a decelerating universe. By comparing luminosity distances and redshifts, they discovered that the cosmic expansion rate was increasing, not slowing under gravity's pull. This surprising result implied the existence of a repulsive component, now called dark energy, constituting about 70% of the universe's energy density and driving acceleration. Type Ia supernova cosmology continues to refine this discovery, with surveys such as the Dark Energy Survey and the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, set to collect tens of thousands of supernova light curves. Improved calibration techniques, accounting for host galaxy properties and dust extinction, are reducing systematic uncertainties, sharpening constraints on the dark energy equation of state parameter W. Combined with complementary probes, supernova studies aim to reveal whether dark energy is a true cosmological constant or a dynamic field evolving over time. Universe's age, combining measurements of the Hubble constant cosmic microwave background anisotropies and the composition of the universe, yields an age of approximately 13.8 billion years. This value arises from integrating the Friedmann equations governing cosmic expansion back to the Big Bang, accounting for the contributions of radiation, matter, and dark energy. The remarkable precision, with uncertainties at the percent level, reflects convergence across independent methods. Cosmic chronometers, globular cluster dating, and white dwarf cooling sequences all corroborate this cosmic timeline. Despite this concordance, tensions in the measured Hubble constant introduce slight discrepancies in the derived age, with locally determined values suggesting a few 100 million years younger universe than the CMB-based inference. Resolving these differences may refine our understanding of the early universe's physics, such as possible contributions from early dark energy or neutrino physics. Ultimately, pinning down the universe's age provides the temporal framework for all cosmic history, from inflation through structure formation to the emergence of life. Look back time. Because light travels at a finite speed, observing distant objects allows us to look back in time. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. This cosmological look-back time enables reconstruction of the universe's history by sampling galaxies and quasars at various redshifts, effectively providing snapshots of different epochs. Surveys that catalog millions of objects across cosmic time trace the evolution of star formation rates, galaxy morphologies, and large-scale structure growth. Interpreting look-back time requires accounting for time dilation and cosmic expansion. Observed durations are stretched by a factor of 1 plus z, affecting light curve measurements and time-dependent phenomena such as supernovae and quasar variability. Precise cosmological models convert redshift into look-back time, allowing astronomers to sequence events, from the Dark Ages through reionization to cosmic noon, and to test theoretical predictions against observational timelines. Look-back time thus transforms the sky into a time machine, revealing the dynamic evolution of the cosmos. Redshift Z quantifies how much the universe has expanded since a photon was emitted. Wavelength stretches by a factor of 1 plus z. In a homogeneous isotropic cosmos, redshift reflects both recessional velocity and cosmic scale factor, linking the observed spectrum of an object to its distance and epoch. The relation between redshift and cosmic time depends on the matter-energy content of the universe, encoded in the Friedmann equations, making Z a fundamental observable for cosmology. Beyond distance estimation, redshift informs the interpretation of spectral features, emission and absorption lines, signature transitions of atoms and molecules shift predictably, allowing identification of chemical composition, ionization state, and physical conditions in galaxies and intergalactic gas. Redshift surveys map the large-scale distribution of matter, revealing baryon acoustic oscillation scales and the cosmic web's filamentary structure. In essence, redshift is the key that unlocks the spatial and temporal dimensions of the universe. Spectroscopic redshift. Spectroscopic redshift determination involves measuring precise wavelengths of known spectral lines, such as the hydrogen-Balmer series or oxygen-forbidden lines, in a galaxy's or quasar's spectrum. Achieving accuracies of delta Z approximately 10 to the power of -4, spectroscopy provides redshift precision necessary for detailed dynamical studies, clustering analyses, and measurements of peculiar velocities. However, obtaining high signal-to-noise spectra requires substantial telescope time and sensitive instrumentation, limiting sample sizes compared to imaging surveys. Spectroscopic surveys like SDSS and DESI have mapped millions of galaxy redshifts, underpinning measurements of the baryon acoustic oscillation signal and redshift space distortions that probe the growth rate of structure. Precision cosmology demands these accurate redshifts to calibrate standard candles, to stack weak lensing signals, and to cross-correlate with other probes. Despite its resource intensity, spectroscopy remains indispensable for unlocking the detailed physics of galaxy evolution and cosmic expansion. Photometric redshift. Photometric redshift estimation uses broadband imaging, measuring fluxes in several filters, to infer redshift based on the overall shape of a galaxy's spectral energy distribution. Machine learning algorithms and template-fitting methods translate color magnitude data into redshift probability distributions, achieving uncertainties of delta Z approximately 0.02 to 0.05 for deep surveys. Photometric redshifts enable redshift estimates for millions to billions of sources, facilitating large-scale structure mapping and weak lensing studies that require vast sky coverage. However, photometric redshifts face challenges from template mismatches, cosmic variance in training sets, and degeneracies between redshift and galaxy type. Systematic biases, such as catastrophic outliers, must be carefully calibrated using overlapping spectroscopic samples. Ongoing efforts combine narrow-band filters, medium-band surveys, and hybrid machine learning approaches to enhance accuracy, striving to balance depth, breadth, and precision for next-generation cosmological analyses. Cosmic variance. Cosmic variance arises because we observe only a single realization of the universe. Statistical fluctuations in matter distribution on the largest scales cannot be averaged out by surveying more area, imposing an intrinsic limit on measurement precision. For phenomena sampling volumes comparable to or smaller than the largest scale fluctuations, such as the cosmic microwave background, low multipoles, or rare high redshift objects, cosmic variance dominates the uncertainty budget. Mitigating cosmic variance involves surveying multiple independent sky regions, combining probes at different scales, and using simulations to model covariance in observables. In galaxy surveys, splitting the sky into disjoint fields and cross-correlating with other traces helps estimate and reduce cosmic variance effects. Recognizing and accounting for cosmic variance is crucial for robust cosmological inferences, ensuring that apparent anomalies reflect true physics rather than the luck of cosmic neighborhood selection. Scalar Spectral Index, N sub s. The Scalar Spectral Index, NSNS, quantifies how the amplitude of primordial density fluctuations varies with scale. In the simplest inflationary models, the power spectrum of curvature perturbations is approximated by Ps, K, Ns1 Ps, to propto K, A, Ns1 Ps, whole K, Ns1, so that Ns1, S1, Ns1 per 1 corresponds to a perfectly scale invariant spectrum, equal power on all scales. Measurements consistently find Ns approximately 0.96 Ns, approximately 0.96 Ns, approximately 0.96, indicating a slight red tilt, more power on larger scales, a telltale signature of slow roll inflation. This deviation from unity arises because the inflaton field's dynamics change subtly as it rolls down its potential, imprinting a scale dependence that reflects the shape of that potential. Determining NNSNS with precision is crucial. Its exact value narrows the class of viable inflationary models. A perfectly scale invariant spectrum, NS equals 1, NES equals 1, NNS equals 1, is disfavored at high significance, whereas many simple monomial potentials predict larger tilts than observed. The sub-percent uncertainties provided by Planck and other experiments thus push theorists toward potentials that yield slightly less scale dependence, such as plateau-like models. Future CMB and large-scale structure surveys aim to tighten delta NS further, sharpening our window onto the microphysics of the inflationary epoch. Tensor-to-scalar ratio R. The tensor-to-scalar ratio, RRR, measures the relative amplitude of primordial gravitational waves, tensor modes, to density fluctuations, scalar modes, generated during inflation. A non-zero RRR would reveal the energy scale of inflation, since the amplitude of tensor perturbation scales as HINF2/MPL2H age IRM INF2M IRM PL2H INF2/MPL2, where HINFH IRM INF is the Hubble parameter during inflation. In simple single-field, slow roll models are approximately 16 epsilon r, with epsilon a slow roll parameter. linking the steepness of the inflaton potential to the strength of gravitational waves. Despite decades of effort, experiments from Bicep, Keck to Planck have only set upper limits. Currently R less than 0.03, R less than 0.03, R less than 0.03 to 0.06, 95% confidence level, ruling out many high-energy models. The hunt continues. A detection of Reheating to the power of -3, 10 to the power of -2 are so Sim 3, E10 2, 10 to the power of -3, 10 to the power of -2 would point to an inflationary energy scale near 10 to the power of 16, GeV, tantalizingly close to grand unification. Next-generation CMB polarization missions, both ground-based, CMB S4, and satellite, Lightbird, aim to probe R down to 10 to the -3rd power, either confirming a primordial gravitational wave background or forcing a paradigm shift toward lower-scale or multi-field inflation scenarios. Acoustic peaks. Acoustic peaks are the striking series of maxima and minima in the cosmic microwave background temperature power spectrum arising from sound waves in the photon baryon plasma prior to recombination. Gravity pulled overdense regions inward, compressing the coupled photon baryon fluid, while radiation pressure pushed back, creating oscillatory modes. At the moment of last scattering, each mode was caught at a particular phase, either compression or rarefaction, imprinting characteristic angular scales, multipoles LLL, onto the sky. These peaks encode a wealth of information. Their positions trace the sound horizon at recombination, their relative heights reveal the baryon-to-photon ratio, and their damping tail constrains the photon diffusion length. Detailed measurement of the first several peaks thus provides precise constraints on cosmological parameters, including the total matter density, baryon density, and expansion history. The acoustic peak structure stands as one of the most compelling validations of the hot Big Bang and inflationary paradigms. First peak, L approximately 220. The first acoustic peak, centered at lambda approximately 220, corresponds to the mode that underwent exactly one compression cycle by the time of recombination. Its angular scale directly measures the ratio of the sound horizon size, roughly 150 megaparsecs, to the angular diameter distance to last scattering. In a flat universe, OTOT equals 1, this ratio places the first peak at approximately 1 degree on the sky, L approximately equals 180 to 220. Observations aligning the peak position so precisely at L approximately 220 L, approximately 220, provide powerful evidence that the universe's spatial curvature is near zero. Beyond geometry, the first peak's height reflects the overall matter content. More dark matter deepens gravitational wells, enhancing compressional amplitude. By combining the peak's position and height, cosmologists infer both the curvature and the dark matter density to percent-level precision. These constraints, when cross-checked against other probes like baryon acoustic oscillations and supernova distances, consistently yield OTOT approximately 1 plus or minus 0.001, OTOT ERM tot naprox 1, RPM 0.001, OTOT 1 plus 0.001, reinforcing the flat LCDM framework. Second and third peaks. The relative heights of the second and third acoustic peaks offer direct insight into the baryon and cold dark matter densities. Baryons add inertia to the photon baryon fluid, amplifying odd peaks, compression, relative to even peaks, rarefaction. Thus, the second peak's suppression compared to the first provides a precise measure of the baryon-to-photon ratio, matching Big Bang nucleosynthesis predictions. Meanwhile, the third peak and beyond probe, the total matter density, including dark matter. More dark matter shifts the matter radiation equality epoch earlier, altering the decay of gravitational potentials and boosting higher-order peaks. The precise measurement of these features by Planck has pinned down OBH squared and OGH squared to sub% accuracy, sculpting our detailed inventory of the universe's contents. Cosmological principle. The cosmological principle asserts that on sufficiently large scales greater than or equal to 100 megaparsecs, the universe is both homogeneous and isotropic. It looks the same in every direction and from every location. This symmetry underpins the Friedmann-Lemaitre-Robertson-Walker metric, the foundation of modern cosmology. While small-scale structure, galaxies, clusters, filaments, and voids abounds, surveys like SDSS and PanSTARRS demonstrate that galaxy clustering statistics converge to uniformity on large scales, validating homogeneity. Isotropy is spectacularly confirmed by the CMB's near-uniform temperature to 1 part in 100,000, save for the dipole due to our motion. Any large-scale anisotropy or preferred direction would manifest as systematic deviations in galaxy number counts or CMB multipoles, yet extensive analyses find no such anomalies beyond cosmic variance. Together, these observations affirm the cosmological principle as a robust guiding assumption for modeling cosmic evolution. Great Attractor. The Great Attractor is a gravitational anomaly in the nearby universe, manifesting as a bulk flow of galaxies, including our local group, toward a region near the Hydra Centaurus supercluster at velocities of a few hundred kilometers per second. Discovered through peculiar velocity surveys in the 1980s and 1990s, it indicates the presence of a massive, yet partly obscured, overdensity lying behind the Milky Way's zone of avoidance. Its mass concentration influences galaxy motions out to tens of megaparsecs, illustrating how large-scale inhomogeneities imprint on local dynamics. More recent work places the Great Attractor within the larger Laniakea supercluster, with the Shapley concentration, at approximately 200 megaparsecs, further biasing flows on even larger scales. Reconciling these contributions remains an active area. Mapping deep infrared and X-ray surveys through the galactic plane seeks to quantify the hidden mass, while constrained simulations model the local flow field. Understanding the Great Attractor illuminates how the cosmic web's most massive nodes continue to shape motions long after initial structure formation. Local group dynamics. Our local group, spanning roughly 1 megaparsec, contains the Milky Way, Andromeda, M31, the Triangulum Galaxy, M33, and dozens of dwarf satellites. Mutual gravitational attraction dominates their motions. Milky Way and Andromeda approach each other at approximately 110 kilometers per second, overcoming cosmic expansion locally. Timing argument calculations. Treating the pair as a two-body system since the Big Bang, estimate the combined mass at approximately 3 times 10 to the 12th solar masses, consistent with independent halo mass estimates from rotation curves and satellite dynamics. Beyond M31, the complex orbits of dwarf galaxies reveal tidal interactions and past mergers, shedding light on the Milky Way's assembly history. Ongoing proper motion measurements by Gaia map these orbits in unprecedented detail, uncovering stellar streams from disrupted dwarfs and constraints on the Milky Way's dark matter halo shape. Together, These studies decode the local group's past and forecast its future evolution within the cosmic web. Andromeda collision, approximately 4 billion years from now. Simulations of the Milky Way-Andromeda encounter, informed by relative velocity and separation measurements, predict a first close passage in about 4 billion years. As their dark matter halos interpenetrate, tidal forces will trigger bursts of star formation, distort galactic disks into tidal tails, and eventually merge cores to form a single, more spheroidal galaxy, often dubbed Milkomeda. During this protracted interaction, lasting a few billion years, gas dynamics and feedback will likely funnel material towards central supermassive black holes, possibly igniting an active galactic nucleus phase. The solar system's fate is uncertain, but benign. While some simulations suggest our sun might be flung into an extended tidal arm, the vast interstellar separations make direct stellar collisions exceedingly improbable. Ultimately, the merger remnant will settle into an elliptical-like galaxy with a thickened stellar halo and depleted gas reservoirs, signaling the end of large-scale star formation in our local environment. Cosmic event horizon. In an accelerating universe dominated by dark energy, a cosmic event horizon emerges. Beyond a certain proper distance, light emitted now will never reach us, no matter how long the universe persists. Unlike the particle horizon, the boundary of what we can see today, the event horizon delineates the ultimate limits of causal contact. Its proper radius is about 16 billion light-years at present, shrinking in co-moving coordinates as dark energy's repulsion accelerates expansion. This horizon implies that distant galaxies crossing beyond it become forever unobservable, isolating bound structures like the local group within an ever smaller observable volume. In the far future, observers will see only the Milky Way's merger remnant, with the rest of the cosmos red-shifted into oblivion. The event horizon thus not only defines our observational limits, but also frames the long-term fate of information and entropy in an ever-expanding universe. Observable radius. The observable universe is defined by the maximum distance from which light has had time to reach us since the Big Bang. Due to cosmic expansion, objects currently at the edge of our observable sphere emitted their light over 13.8 billion years ago. But because space has stretched, their present proper distance is about 46 billion light-years. This boundary, often called the particle horizon, marks the limit of our direct observational reach. Beyond it, light is still en route, meaning we cannot yet see those regions. Although the observable radius sets a hard cap on what we can detect today, it grows with time as light from ever more distant regions arrives. Yet, owing to the universe's accelerating expansion, there exists an event horizon, roughly 16 billion light-years proper distance, beyond which events occurring now will never be observable. Thus, while the particle horizon defines how far we've seen, the event horizon prescribes how far we ever can, even given infinite time. Multiverse theories. Multiverse theories propose that our cosmos is just one bubble within a vast ensemble of universes, each potentially governed by different physical constants, laws, or dimensions. These ideas arise naturally in several frameworks. Eternal inflation suggests that inflationary expansion never ends globally, spawning an infinite collection of pocket universes. String theory's landscape of vacuum solutions implies a staggering number of possible low-energy configurations, and quantum cosmology entertains branching universes via the many worlds interpretation. While tantalizing, multiverse concepts pose profound challenges for empirical science, since direct observation of other universes may lie forever beyond our cosmic horizon. Nevertheless, some suggest that subtle signatures, such as anomalous cold spots or ring-like patterns in the cosmic microwave background, could betray collisions or interactions with neighboring bubbles. Testing multiverse ideas therefore requires pushing observational precision to extremes and confronting deep questions about the nature of scientific inference and falsifiability. Eternal inflation. Eternal inflation extends the inflationary paradigm by revealing that while inflation ended within our patch of the cosmos, it continues unabated elsewhere. Quantum fluctuations of the inflaton field can locally delay its decay, causing some regions to keep inflating exponentially. In this self-reproducing process, new inflationary domains, or bubbles, continually pinch off, each potentially evolving into a distinct universe with its own physics. This mechanism elegantly explains why our observable universe underwent a finite inflationary epoch, ending when our local inflaton field decayed, while the greater multiverse persists indefinitely. However, eternal inflation gives rise to the measure problem. In an infinite multiverse, how does one assign probabilities to events or properties when every outcome occurs infinitely many times? Resolving this requires novel approaches to regularizing infinities and may ultimately reshape our understanding of cosmic initial conditions and anthropic reasoning. Possible cosmic fates. The ultimate destiny of the cosmos depends on the interplay of its energy components and their dynamics. In a Big Rip scenario, dark energy with an equation of state parameter W less than -1 grows inexorably, tearing apart galaxies, stars, planets, and eventually atomic nuclei as expansion accelerates without bound. By contrast, heat death, or the Big Freeze, envisions a universe drifting into emptiness. Dark energy-driven acceleration disperses matter. Stars exhaust their fuel, black holes evaporate via Hawking radiation, and entropy maximizes, leaving a cold, dilute, and lifeless expanse. Alternatively, if dark energy is transient or reverses sign, the universe could undergo a big crunch. Expansion halts and reverses, culminating in a cataclysmic collapse back to high density and temperature. The Big Bounce hypothesis posits that such a collapse might trigger a new expansion phase, yielding cyclic cosmologies. Current observations, favoring W approximately -1, strongly support an everlasting accelerated expansion, making heat death the most likely outcome. But refining dark energy's nature remains crucial to pinning down our cosmic future. Spatial flatness. Spatial flatness refers to the universe's curvature parameter, omega k, being extremely close to zero, meaning parallel light rays remain parallel and Euclidean geometry holds on cosmic scales. Inflationary models predict this outcome. Exponential expansion dilutes any initial curvature to negligible levels. Precision measurements of the cosmic microwave background's acoustic peak positions by Planck and WMAP confirm flatness to within about 1%. Absolute value of omega k less than or equal to 0.01. Tightening earlier, looser constraints. This near-perfect flatness has deep implications. It demands that whatever pre-inflation curvature existed was extraordinarily fine-tuned, supporting the necessity of an inflationary phase. Moreover, flatness simplifies cosmological modeling, allowing the Friedmann equations to focus on matter and dark energy contributions without curvature terms. Future surveys combining large-scale structure, gravitational lensing, and next-generation CMB polarization aim to push the flatness constraint to even tighter limits, probing potential subtle departures that could hint at new physics. Cosmic isotropy. Cosmic isotropy means the universe looks statistically the same in every direction. The cosmic microwave background's temperature is uniform to 1 part in 100,000, delta T by T, approximately 10 to the power of -5, across the entire sky, apart from the dipole anisotropy caused by our motion, indicating remarkable isotropy. Such uniformity underpins the cosmological principle and justifies modeling the universe with homogeneous and isotropic geometry on large scales, while tiny anomalies, like the CMB's cold spot or hemispheric power asymmetry, have sparked debate. None have withstood rigorous statistical scrutiny to overturn isotropy. Large galaxy surveys also show that beyond scales of approximately 100 megaparsecs, galaxy distributions approach homogeneity and isotropy, with local clustering fading into uniformity. Ongoing and future sky mapping missions will examine isotropy at unprecedented depth, searching for any directional signatures of cosmic defects or large-scale flows. Primordial magnetic fields. Magnetic fields permeate galaxies and clusters today, but their primordial origins remain elusive. Several mechanisms have been proposed for seeding cosmic magnetism. Quantum fluctuations of the electromagnetic field during inflation can generate near-scale invariant magnetic spectra. Phase transitions, electroweak or QCD, may produce magnetic domains via charged particle currents, and astrophysical battery effects, such as the Biermann battery and ionization fronts, can create small seed fields that later amplify via dynamo action. Detecting primordial magnetic fields directly is challenging, but they would imprint signatures on the cosmic microwave background's polarization, Faraday rotation, and on the formation of large-scale structure. Current limits from Planck constrain the comoving field strength to less than 1 nanogauss on megaparsec scales, yet next-generation CMB experiments and 21-centimeter line observations could push sensitivities into the picogauss regime. Uncovering primordial magnetism would illuminate the coupling between fundamental forces and cosmic evolution in the universe's earliest moments. Cosmic string searches. Cosmic strings are one-dimensional topological defects predicted by certain field theories during early universe symmetry breakings, carrying energy density proportional to their tension mu. If real, they would produce distinct gravitational signatures, line discontinuities in the CMB, gravitational lensing events, creating double images without time delay, and stochastic backgrounds of gravitational waves from oscillating string loops. Extensive searches, including high-resolution CMB analyses by Planck, deep optical surveys for lensing signatures, and pulsar timing arrays probing nanohertz gravitational waves, have found no conclusive evidence for cosmic strings, placing upper limits on their tension of G less than 10 to the power of -7. Future gravitational wave observatories, e.g. LISA, and refined CMB polarization maps aim to tighten these constraints further, or perhaps uncover faint string signals, testing theories of early universe phase transitions. Next-generation observatories. The James Webb Space Telescope, JWST, launched in December 2021, peers into the first few 100 million years after the Big Bang, capturing infrared light from the earliest galaxies and revealing their formation pathways. Its deep fields and spectroscopic instruments probe star formation rates, galactic assembly, and reionization-era physics with unparalleled sensitivity. Meanwhile, the Euclid mission, ESA, and NASA's Roman Space Telescope will survey billions of galaxies across large sky areas to map dark energy and dark matter via weak lensing and galaxy clustering. Euclid's optical and near-infrared imaging and spectroscopy will chart structure growth to redshift Z approximately 2, while Raman's wide field and high resolution will complement JWST's deep, narrow focus. Together, these observatories promise a comprehensive view of cosmic history from reionization through cosmic noon to dark energy's accelerated expansion. Parameter refinement. Cosmological parameters such as the Hubble constant, matter densities, spectral indices, and dark energy equation of state are currently measured to percent-level precision or better. Yet tensions, like the differing H0 values from local and early universe probes, underscore the need for continued refinement. Improved measurements aim to resolve these discrepancies and test for subtle extensions to the lambda CDM model. Forthcoming surveys, CMB S4, the Vera C. Rubin Observatory's LSST, DESI, and 21-centimeter experiments will dramatically increase data volume and quality. By combining independent probes, supernovae, BAO, lensing, intensity mapping, cosmologists will cross-validate results, reduce systematic errors, and tighten constraints on neutrino masses, dark energy dynamics, inflationary parameters, and potential new physics. This relentless drive toward precision will sharpen our picture of the universe's origin, composition, and ultimate fate.